My name is Ryan Novak, and I'm a senior scientist with ERG. Unfortunately, I was not able to travel from Virginia to join you all in person today. For over 10 years, I've been supporting the U.S. EPA and state regulators with collecting and analyzing data on PFAS use, release, and treatment. Today, I'll be discussing a pilot study we conducted for the New Mexico Environment Department. This project yielded the first state-sponsored analysis of PFAS in landfill leachate and on-site groundwater wells in New Mexico. Before we dive into the study, I do want to ground us in the reality of a landfill's role in the PFAS cycle. PFAS have exceptional stability and some unique characteristics because of the carbon-fluorine bond and the high electronegativity of the fluorine atom. These properties make PFAS desirable in many consumer products and industrial processes. However, they also make them persistent and mobile in the environment. When we throw away products made with PFAS, most of it ends up in a landfill. And even though landfills didn't manufacture or use these chemicals, they are now responsible for managing them. The problem is that if any of the leachate or gas escapes the landfill, there is a risk of surface water, groundwater, or other environmental media contamination. Safely managing PFAS waste is among the most urgent technical and regulatory challenges the waste management industry faces. And this isn't just a theoretical risk. The headlines you see on the screen represent a growing wave of public and regulatory scrutiny across the country. The waste industry's challenge is now moving from simply receiving these PFAS-containing materials to understanding and mitigating how they might escape into the environment. The New Mexico Environment Department is trying to stay ahead of the curve by proactively investigating and addressing known PFAS contamination across the state. As part of this 2025 effort, the NMED Resource Recovery Bureau launched an initial pilot study specifically for landfills. ERG was brought in to provide the technical, sampling, and data analysis support, with sample analysis conducted by partners at Battelle. The objectives of this study were threefold. First, we wanted to establish a baseline. We set out to determine the actual levels of various PFAS within the leachate and the surrounding groundwater. Second, we wanted to review available information to distinguish between potential groundwater contamination from the landfill and what might be migrating from off-site sources. And finally, all this leads to risk management. We're evaluating how these concentrations and sources impact the potential risks to the state's groundwater resources. To put this study into practice, we engaged 3 volunteer landfill sites. We'll refer to these as sites A, B, and C for this presentation. They were selected to give us a look at different geographic regions across New Mexico, and while the locations varied, their technical DNA was quite similar, which helped us control for certain variables. All 3 have been operating for roughly 30 years. All 3 utilize composite liner designs, and they accept similar waste profiles, which include municipal solid waste, wastewater sludges, and various industrial waste. None of these landfills discharge to a surface water or a publicly owned treatment works. Rather, all the leachate generated on site was captured and recycled on site or evaporated. Before hitting the field to collect samples, we performed a desktop review for each site. This included characterizing the local geology and the monitoring well network. But more importantly, we also did initial screening of potential off-site PFAS sources within a 10-mile radius. ERG conducted the field sampling, pulling leachate directly from existing leachate extraction points, and we pumped groundwater from on-site monitoring wells. To ensure that we could differentiate between background levels and potential site impacts, we sampled at least 1 upgradient and 1 downgradient well at each facility. And for the lab work, we utilized EPA Method 1633. Right now, this is the gold standard for non-potable water, and it allowed us to detect and quantify 40 different PFAS analytes. So our primary goal was to establish baseline data. But it's important to remember a detection of PFAS in the groundwater does not automatically mean that the landfill is the source. And while we did not perform a full forensic investigation for any specific site as part of this pilot study, we did do this desktop analysis. We used EPA's PFAS analytical tools to pull from national databases, including ECHO, and it flags industry sectors known to handle PFAS. These include, but are not limited to, chromium plating and anodizing shops, textile mills, food contact paper mills, firefighting training centers, airports, and then specialized fluorochemical and plastic manufacturing plants. The map on the slide gives you a sense of the density of these potential sources across New Mexico. And I do want to emphasize that the EPA tool we use, it flags these facilities based on industrial category. It does not necessarily mean that they have a confirmed PFAS release. To truly identify where PFAS contamination in groundwater is coming from, we would need to consider several additional pieces of information, including groundwater flow, the specific chemical signature observed in the groundwater, and history at the site. And while this pilot didn't go that deep, we are using this multiple lines of evidence approach for other locations where PFAS contamination is found. We sent a team to collect leachate and groundwater samples from each site, following strict sampling protocols, including low flow, deep well extraction, clean hands, dirty hands, etc. Our biggest field challenge was the existing hardware. So these on-site pumps contain non-removable Teflon O-rings and other fluoropolymer components. We addressed that through QA/QC samples. All of our field and equipment blanks confirmed zero cross-contamination. Additionally, because the wells at Site C were dry, we did adjust our scope to focus exclusively on leachate characterization for that location. On the analytical side, we shipped the collected samples to Patel, who ran EPA Method 1633. And to provide regulatory context and assess potential risk, we benchmarked our groundwater results against 5 PFAS MCLs EPA promulgated in 2024. These compounds being PFOA, PFOS, PFHXS, PFNA, and HFPODA. And now we'll dive into the leachate sample results. Unsurprisingly, we did detect PFAS in the leachate at all 3 sites. Looking at the plot, you'll see the mean concentrations for the 5 MCL PFAS, as well as the sum of measured PFAS. The sum of the 40 measured PFAS range from as low as 3,700 parts per trillion at Site A to above 30,000 parts per trillion at Site C. Fluorotelomere carboxylic acids were the most prevalent PFAS detected at all 3 sites, specifically 5,3 FTCA and to a lesser extent 3,3 FTCA. These 2 PFAS alone represent more than half of the total measured PFAS in the leachate at these sites. For the most part, the concentrations and chemical distributions we observed were consistent with what we've seen in literature, and then U.S. EPA data for municipal solid waste landfill leachate. The Site C leachate PFAS concentrations were notably higher than sites A or B. Digging deeper into the data, this is largely because the FTCAs were a magnitude higher than the other 2 sites. So the variance could stem from several factors, including the specific types of industrial waste that Site C receives, differences in waste age and landfill conditions, or even weather conditions shortly before the sampling episode. Pivoting to the groundwater results for sites A and B and how they compare to the EPA's MCLs. Those MCLs are shown here on the slide. I do want to note that EPA is currently reconsidering and may rescind some of these MCLs, including the ones for PFNA, PFHXS, and HFPODA. This plan view of Site A shows our up gradient well at the bottom and the 2 down gradient wells at the top, following a north-northwest groundwater flow. The results here were encouraging. We saw non-detects for all PFAS in the up gradient well, as well as one of the down gradient wells. In the second down gradient well, we found trace detections of PFOA at about 1.6 parts per trillion, as well as several other short chain PFCAs below 2 parts per trillion. At Site B, the groundwater flow here is from west to east. You can see our up gradient well on the left and the 2 down gradient wells on the right. We did detect PFOS in the up gradient well as well as one of the down gradient wells at this site. However, in both instances, the concentrations remained well below 4 parts per trillion MCL. The presence of PFOS upgrading is a key data point here. It reinforces the idea that we need to look at the broader geographic context, as this PFOS maybe didn't originate from the landfill cell. The key takeaway for both sites was that the groundwater concentrations are orders of magnitude lower than what we measured in the site's leachate and below the MCL values, suggesting that the current engineering controls in place at these landfills are performing effectively. Although we didn't identify substantial groundwater presence at either site, I'm going to walk through some of the preliminary review of the on-site and off-site sources that could have impacted our groundwater results. When we look at these sites, it's important to remember that they rarely exist in a vacuum and they're pretty complex hubs. Beyond the landfill cell, there are other routine waste management activities that can contribute to PFAS detections. For example, here with Site A, the yellow box is around a composting facility. Many of these compostable food containers and wrappers contain PFAS, and since composting areas are typically unlined like this one, decades of operation can create a potential pathway to groundwater. Additionally, many landfill routine operations like dust suppression using leachate can have a cumulative impact. We also looked outside the property line. So using a 10-mile radius, we identified 19 potential sources around Site A, ranging from airports to wastewater treatment facilities. Based on the current groundwater contour data, several of these potential sources do appear to be located up gradient of the landfill. And while this suggests the potential for offsite contribution, recall we didn't see any notable PFAS concentrations in the groundwater samples. However, had we identified some, identifying these neighbors would have been a vital first step in that multiple lines of evidence approach. At Site B, the landscape's much more remote. We only had 3 potential sources within a 10-mile radius. If we look at the hydraulic gradient, we have another waste management facility located upstream of the landfill, and then there's a industrial site situated just about 2 miles downstream. For this effort, identifying these neighbors really wasn't about assigning blame. It was about having context for any of our potential detections. To wrap up, this pilot study provided the first state-specific PFAS data and established a baseline for New Mexico's landfills and their on-site groundwater. Our findings showed that the municipal leachate was dominated by FTCAs with concentrations that align closely to what we've seen in national data sets. More importantly, the groundwater detections were all below the 2024 MCLs, which is a strong indicator that the current landfill engineering controls are doing their job. However, this single snapshot is just the beginning. Because the detections were low and infrequent, we did not perform any forensic dives in this pilot, but that is where we are heading next. Moving forward, we will be expanding our sampling to include more sites and looking at how waste age and type influence levels over time. To get a fuller picture, we're also integrating non-targeted analysis paired with AI-driven forensic tools. The use of non-targeted analysis will allow us to account for hidden precursor compounds that method 1633 does not measure. And then we're also deploying tools to compare the PFAS profile of a site's groundwater sample against a massive database of known signatures from different sources, sort of like matching a fingerprint. So when we pair that with the nearby source information, we can take it from just screening for potential sources to true source attribution. That is all I had prepared today. I appreciate your time and the opportunity to present. If we have time, I'm happy to take any questions.
Thank you. We do have time for a couple questions. We have one coming.
Are you aware of what the landfills do with their leachate?
Yes, at these particular sites, they are collected. Most of it is reused for dust suppression on site, so it's reapplied to the landfill. Leachate that is not used for dust suppression is sent to an evaporation pool. There is no discharge at these sites.
Any other questions? Yep, we have one more.
Hi, a couple questions. Are these sites closed landfills or active landfills?
These are active landfills, and they are MSW landfills, non-hazardous.
Okay. And then once the liquid has been evaporated from the leachate ponds, what do they do with the sludge?
I actually do not know. I can follow up, but I do not know off the cuff.
Okay.